Welcome to the presentation of Chapter 1, Introduction. We will study the following topics in this chapter: foundations, soils and superstructures, classification of foundations, shallow foundations, deep foundations, selection of type of foundations, general guidelines for design, modeling, parameters, analysis and design criteria, and soil maps. The presentation is done through slides and audio narration as an option for detailed explanation of the topic shown in this slide. The narration is done using two of the guest voices available in the software. However, the first slide includes the option of few more direct audio narrations. Have a good time and enjoy the presentation. Foundations are essential to transfer the loads coming from the superstructure such as buildings, bridges, dams, highways, walls, tunnels, towers, and for that matter, every engineering structure.
Generally, that part of the structure above the foundation and extending above the ground level is referred to as superstructure. The foundations in turn are supported by soil medium below. Thus, soil is also the foundation for the structure and bears the entire load coming from above. Hence, the structural foundation and the soil together are also referred to as the substructure. The substructure is generally below the superstructure and refers to that part of the system that is below ground level. The structural foundation interfaces the superstructure and the soil below as shown in figures 1.1 and 1.2. The soil supporting the entire structure above is also referred to as subsoil and/or subgrade. For a satisfactory performance of the superstructure, a proper foundation is essential. The man-made superstructures or facilities utilities are expected to become very intricate and complex depending on creativity, architecture and infinite scope in modern times. However, the soil medium is Mother Earth, which is a natural element, and very little can be manipulated to achieve the desirable engineering properties to carry the large loads transmitted by the superstructure through the interfacing structural foundation, which is usually referred to as foundation. Further, almost all problems involving soils are statically indeterminate. Lamb and Whitman, 1998, and soils have very complex behavior. Foundation design becomes a challenging task to provide a safe interface between the man-made superstructure and the natural soil media whose characteristics have limited scope for manipulation. Hence, the above factors make every foundation or soil problem very unique, which may not have exact solution. The generally insufficient and conflicting soil data, selection of proper design parameters for design, the anticipated mode for design, the perception of a proper solution and so on require a high degree of intuition, that is, engineering judgment. Thus, foundation engineering is a complex blend of soil mechanics as a science and its practice through foundation engineering as an art. This may be also referred to as geotechnique or geotechnical engineering. Foundations are classified as shallow and deep foundations based on the depth at which the load is transmitted to the underlying and/or surrounding soil by the foundation as follows. A typical shallow foundation is shown figure 1.3a. If dF/B is smaller or equal to 1, the foundations are called shallow foundations, where dF equals depth of foundation below ground level, and B equals width of the foundation, least dimension. Common types of shallow foundations are continuous wall footing, spread footing, combined footing, strap footing, grillage foundation, raft or mat foundation, and so on. The shallow foundations are thus used to spread the load pressure coming from the column or superstructure, which is several times the safe bearing pressure of supporting soil, horizontally, so that it is transmitted at a level that the soil can safely support. These are used when the natural soil at the site has reasonable safe bearing capacity, acceptable compressibility, and the column loads are not very high. A typical deep foundation is shown in Figure 1.3b. If dF/B is bigger or equal to 1, the foundations are called deep foundations, such as piles, drilled piers, caissons, well foundations, large diameter piers, and pile raft systems. Deep foundations are similar to shallow foundations except that the load coming from columns or superstructure is transferred to the soil vertically. These are used when column loads are very large. The topsoils are weak and soils with a good strength and compressibility characteristics are at a reasonable depth below ground level. Further, earth-retaining structures are also classified under deep foundations. While engineering judgment and cost play a very important role in selecting a proper foundation for design, the guidelines given in Table 1.1 can be helpful. Following broad guidelines may be useful for foundation design and construction, depending on site. 1. Footings should be constructed at adequate depth below ground level to avoid passive failure of the adjacent soil by heaving. 2. The footing depth should be preferably below the zone of seasonal volume changes due to freezing, thawing, frost action and groundwater, and so on. 3. Adequate precautions have to be taken to cater for expansive soils causing swelling pressure, upward pressure on the footing. 4. The stability of the footing has to be ensured against overturning, sliding, uplift, flotation, tension at the contact surface, base of the footing, excessive settlement and bearing capacity of soil. 5. The foundation needs to be protected against corrosion and other harmful materials that may be present in the soil at site. 6. The design should have enough flexibility to take care of modifications of the superstructure at a later stage or unanticipated site conditions. All practical problems need to be reduced to physical models and behavior represented by corresponding analytical equations. The physical parameters of the system form the inputs in the mathematical equations for computing the responses. The models used should be simple enough that the physical parameters needed for computations are accurately and reliably determined using inexpensive test procedures. For example, in a foundation soil system, the foundation can be modeled as rigid, while the soil may be assumed to be elastic. The physical parameters needed in such a model are the elasticity parameters of the soil, that is, Young's modulus of elasticity, E and Poisson's ratio, V of soil. Naturally, E and have to be accurately determined for the soil under consideration as they will be needed for the computation of the responses of the system. Thus modeling, evaluation of parameters and analysis are closely linked and the solutions obtained are highly dependent on all these aspects. The responses thus obtained have to be judged using appropriate design criteria specified either by codes or evolved out of practice and/or experience. The design process necessarily has two vital components, namely the methods of analysis and experimental data, which have to be integrated with them to yield accurate results. However, Both the methods and data depend entirely on the mechanism chosen for mathematical idealization of the system components. At this juncture, engineering judgment and experience is very useful. It may be noted that optimum accuracy in analysis and design can be achieved only by properly matching the data and analytical methods used. It is also obvious that any improvement either in the data alone or any sophistication in analytical methods alone can even reduce the accuracy of the results predictions. Most countries prepared the maps of soil deposits, based on the geological and geotechnical data available. These are very useful for a quick assessment of the project and its requirements. A map of soil deposits in India is given in Figure 1.4.
Let us summarize the topic presented in this chapter. In this chapter, the common terms used in foundation design, that is, foundations, soils, superstructure and substructure, etc., have been explained. Classification of foundations as shallow and deep foundations is introduced. General guidelines for selection of type of foundations and their design have been outlined. The importance of modeling, parameters, analysis and design criteria are emphasized. The use and importance of soil maps of each country is brought out. In the next chapter, we will review the engineering properties of soils which are needed for the foundation design and analysis. The methods of soil exploration, sampling and testing of the soils at site for determining these parameters are also discussed. Thanks and have a good day.